And so if you have two resistors which have the same current, then notice the voltage must be proportional to the resistance. In other words, if the ratio of resistance here is 1:2, the ratio of voltage here must also be 1:2. So if the voltage here is X, the voltage here must be 2X. Same is the case here. If the voltage here is X, the voltage over here must also be 2X. And that means I can now immediately calculate what the voltage is. Because I know 9 has to be divided in the ratio of 1:2. And when you divide that into 1:2, you get 3 and 6. And that's why I took 9, because it's easy to divide that. But you could have taken any values of the voltage. And the same will be over here. Here also, this would be divided in the 1:3 ratio. 3 volts and 6 volts. So voltages get divided equally because the ratios are the same. So what? What does that do? Well, now let's look at the voltages at these 2 points. To do that, remember, whatever is the voltage here, same is the voltage here. So the voltage here and here is exactly the same, isn't it? If you want to call that as 9 and you want to call this as 0, then this would be 9 and this would be 9 as well. Now notice when I go from here to here, there's a 3 volt drop. But when I go from here to here, there's again a 3 volt drop. Meaning, these 2 points must also have the same voltage. So, voltage at point A must exactly equal voltage at point B. That's the consequence of having the same ratios of the resistance. So what, you ask? Well, now notice, because the voltages are exactly the same over here, if I were to go ahead and now, in this circuit, when it's running, if I were to put a resistor in between, or a capacitor in between, doesn't matter what you put in between, notice the voltage across it is the same, therefore, these two voltages are the same, therefore the potential difference is 0. There is no difference in voltage, there is no potential difference, and therefore there will be no current flowing over here. And that's why a balanced Wheatstone's network has no current. Does that make sense? Isn't that wonderful? The whole idea is when the ratio of the resistances are the same, the voltage also gets divided in the same resistance, and therefore these 2 points will end up with the same voltage, making sure there is no potential difference. That's why the current goes to 0. And now hopefully you'll agree that it doesn't matter what voltage you put over here, what are the values of the resistances over here or over here. All that matters is that the ratio here must be exactly the same as the ratio over here, and then you will find no current flowing in between. Now you might ask, okay, so what's the application of this? Why should I care about this? Well, this network is used in calculating practically values of unknown resistors. For example, let's say there is a wire over here, there's some object over here whose resistance we don't know and we want to calculate it. What we can now do is we can set up a Wheatstone's network like this, and instead of a red resistor over here, we can put a galvanometer. A galvanometer basically detects current. It will tell you if there's a current here or not. And then we can take one of these resistors as a variable resistor, something that's resistance can be changed. And now, all you have to do is keep changing this resistance and look at the value of the galvanometer. So as you keep changing this resistance, let's say the galvanometer the value becomes 0 when you hit, maybe 7 ohms. When this goes to 7 ohms, let's say the current over here goes to 0. Now I know, this Wheatstone network is balanced. Therefore, the resistance here must be exactly, the ratio here must be exactly the ratio here. And then this is 1:7, this must be 1:7, so the resistance over here is 7 times 5, 35 ohms. Amazing, right? So you can use this, and we will use this in a future video called Meter Bridge to explore how to use Wheatstone's network in practice to calculate unknown resistance. Now we could stop over here, but I want to go one step forward and generalize this, something that might help you in your competitive exams. So let me bring back the original circuit. My question to you is, do you think that this circuit can be extended? Let's say I add more resistances over here. Something like this. What do you think about this one? Would this also be balanced? It's a more complicated circuit now, but would it be balanced? Would the current here and here be also 0? Can you pause and think a little bit about this? Alright, let's see. We can apply the same logic. The first step is to first neglect the resistances and then see how the voltage gets divided. Now notice that the ratios of the resistances here is exactly the same as over here. 1 is to 2 is to 5, 1 is to 2 is to 5. Which means the voltages will also get divided similarly, right? 1 is to 2 is to 5, 1 is to 2 is to 5. And therefore, the voltage drops will be the same, just like before. And that means the voltages here must be the same as here. Voltages here must be the same as over here. In other words, there will be no current flowing over here. Which means you can solve the same circuit here as well. Beautiful, right? Extended Wheatstone's network, something you might see in JEE. Let me show you another way in which we can extend this circuit. What if we extend the circuit this way? What do you think about it now? Again, pause the video. I know it looks very complicated, but pause the video and think a little bit about it. The batteries are connected across this and this. Alright, again notice we can use the same logic. If you forget about these resistors in between, then the voltage should get divided equally because again, they have the same ratio. 1 is to 2, 1 is to 2, 1 is to 2. And therefore, the voltages here, here, and here must be the same. So no current will flow over here. And so you can neglect this and you can solve this circuit. If I hadn't given you the color coding, just look at how complex this looks like. Typical, competitive exams problem. Looks very complex, but by using the same logic of Wheatstone's network, you can solve it. So long story short, a basic Wheatstone network is 4 resistances connected this way with a resistance in between. It's balanced when the resistances are in the same ratio. When that happens, the voltages get divided equally, and therefore the voltage across this red resistor becomes the same. No potential difference, no current flows through it. Balanced Wheatstone network.